Welcome to the fifth and final video in the Day of Datomic training series. In this final video, Stu covers the operational characteristics of Datomic along with the issues that you need to be aware of when planning your system. Stu also covers caching in Datomic, as well as indexes and the indexing process, choosing a storage service, and monitoring your Datomic system. Finally, Stu finishes out with a discussion of Datomic capacity planning.
We've looked at the information model of Datomic, which I would characterize importantly as accumulate only and granular, right? It's a very granular thing to have a single universal schema of 5 tuples as opposed to multiple relations as you might have in a SQL database. We have looked at Datomic's schema, which is attribute scoped. So you don't say things about the relationships between attributes. You only say things about attributes, which is very open and flexible, and on the positive side, makes it very easy to build systems that will not break. And on the negative side, doesn't allow you to do some of the kinds of enforcement that a traditional relational system could do. We've looked at Datomic's transactional model, which is awesome. Just bar none, ACID transactions are fantastic for making systems that you can reason about. And unlike a lot of NoSQLs, it's ACID. Unlike even relational databases, there aren't any knobs that are like, I want to just totally flush ACID down the toilet in order to win some benchmark, right? We don't care, right? I want to win people having systems that they understand and can reason about. And the combination of accumulate only and ACID transactions is an incredible pairing for building robust systems. We've looked at query, and we've looked at how query allows you to have data log, which has the expressive power of the relational algebra behind SQL, but how data log matches really nicely with the positional nature of Datomic. So it's really easy to read a query, even if it has 15 different clauses. You can just go, the skull is connected to the skeleton, and the hip bone is connected to the thigh bone, and so on and so forth. And it's very easy to read because you don't have all of the extra indirection of naming tables and having to name things. And because everything has the same shape, you can take advantage of positionality. You can imagine, I mean, the flip side of this argument is imagine how much data log, as it's construed like in Datomic, would stink against a relational database where you had a 17-column long thing with, and you're having to read it and go, is that column 13 or is that column 14? Right? It wouldn't be a good match. So, but it, like with many things, it's the combination of things that really makes sense, and not necessarily the individual items. We've looked at the power of pull, which allows you to make hierarchical selections and navigate both sort of forwards and backwards through your data. We've talked about how Datomic's indexes allow a really nice sweet spot for a variety of cases that overlap with things that people do traditionally with SQL stores or with graph databases or with document stores, what have you. Now we're going to talk about what it's like to put Datomic into production. So what are the operational characteristics of it, and how is that going to affect the suitability of Datomic or non-suitability for a particular project? So we're going to look at the peer model. We're going to look at how Datomic builds indexes. We're going to look at storage and where Datomic can store data, and how you will run and monitor transactions, and how you'll capacity plan for your system. So the first thing to note is that Datomic distributes query. Right? Query fundamentally is distributed in Datomic. It happens in one or more peers, or it happens in one or more peer servers. Or you can mix peers and peer servers. So we haven't said that before, but it's worth saying. Right? The same Datomic system could have peers where you want to take advantage of the intimacy and being on the JVM, and you could have peer servers where you want to have lighter weight processes, connecting to the peer server. We've focused mostly today on working with clients, but let me make the argument briefly for peers. Peers take advantage of co-locating query with your app. When you co-locate query with your app, there are a lot of other things that you might do. For one thing, you might bring your own query functions. So you can actually write functions in Clojure or Java or Scala or what have you. And because your application process space is the query process space, you can call those functions inside query. I didn't show that earlier. It's not a client feature. But in peer land, you can say, I want to write my own functions and then use them inside of query. Also, today, peers allow you to install and run transaction functions. With peers, in addition to the pull API, there's also an API called the entity API. The entity API is lazy. So you just say, give me an entity, and then you start asking for attributes. And if they're not already present in the cached indexes on your local process. They'll be fetched, and you keep navigating. And this allows you to just wander around your data. It's very nice for exploratory use. Pull is probably better when you're in production, when you sort of should have a commitment to what you want. But entities are really nice for just wandering around. The peer also has APIs that reflect directly against the database. So there are APIs on the peer that say turn an ident into an entity ID, or turn an entity ID into an ident, those kinds of things. Those things you can do with query, right? So the clients are capable of doing them, but the peers are capable of doing them, several orders of magnitude faster because they're direct in-memory lookup. Also, with peers, you can do cross-database joins. And I don't mean just passing the sort of current value and a different older value of a database. I mean a completely different database. You could serve more than one database. And because the peer controls the query address space, it can say, I want to connect to this transactor and to that transactor and join across them. Peers also give you control over partitions because they have access to structural temp IDs, not just the string temp IDs that we have with clients. So all of that stuff, if you want all those things, peers are going to be nice for you. Peers let you bring your own transaction functions. So instead of just add and retract, you could write your own update function. So here, John's balance wants to go from 100 to 110, but you'd like to write that as a function called increment. Increment is just another operation against the database that you write and install on your transactor. And transaction functions run inside the transaction, and they have access to the entire value of the database at the time of the transaction. That's their special power. And then they just have to expand. When you write one of these, it just has to expand from inc John balance 10 to db add John balance 110. Well, how does it figure out balance 110? It's able to look in the database because it has access to the database at the time of the transaction. So it can say, I want to look up inc, return that function. That function then is going to get called with a database value. It's going to be able to look into the database value, look at its arguments, John account 10. It's going to be able to see that the current value is 100, and then the job of a transaction function is just to emit more data. So the closest thing to transaction functions that you might be familiar with is actually macro expansion in a language like Clojure, right? It has some data. We're going to expand it into some other data. And they're quite easy to write. You can even write them in Java quite simply. So here's inc. What does inc have to do? Inc has to look up the entity in the database, find the old balance, calculate the new balance, create an assertion, and return a list creating that assertion. So there's the actual implementation. This is not using Clojure now. This is using Java. But grab the entity out of the database, look up the amount from that entity, grab the attribute, add the amount, then manufacture a list that has in it db add entity attribute value, and then return that list wrapped up as transaction data. On the other hand, peers also bring more responsibility. Your program is less portable, right? It's now dependent on your transaction functions, which are admittedly in your database, but they're not in every database. You're going to have a bigger code footprint because you have to have a library in your application that can talk not just to a service, but also to the storage service, right, to the underlying storage. You're going to have a bigger memory footprint, and this is actually kind of double down, right? You're in the JVM, which is a big memory footprint anyway, and the peer runs better with more memory because it can hold a big cache of stuff. So there's an advantage to making big processes, which is fine. Big processes are okay, but if you don't want a big process, then that's not so great. And the API is an in-process synchronous API. The other thing, there's a subtlety here that people are sometimes don't think through when they start using peers, is that in a traditional database, in any kind of client-server system, then flow control is going to be imposed upon you by the system that you're talking to. Right? If you overwhelm it, it's going to say, oh, you're hurting me. Stop doing that. And the peer server will do that. So when you're talking with a client to the peer server is configured with a maximum number of concurrent in-flight operations when you start it. And if you put more operations in flight than that, you're going to get back an anomaly that says, sorry, talk to the hand, you have to wait. With the peer, this is a synchronous in-process API. This means you have the power and the responsibility to do that pushback. Because there's now nobody between you There's not a process in between you that's going to say talk to the hand, right? We could have done that, right? We could have made the peer library have some kind of thing in it that pushes back on you, but that's just, tying your own hands in your own application. You should be in charge of that, but the other implication is you must be in charge of that. So you have to decide, how many queries you want to allow in flight and put your own policy in place, because you have the ability to control that, but you got to use that ability.
Can you auto kick off another peer that time to say for account for load?
So Jay's question is, can you, I love questions with pronouns, can you auto kick off a peer when something happens? For some values of you, yes. There are some use there are some use that can do that, and there are other use that can't. So I mean, it's definitely the benefits and the weaknesses of commingling, right? Yes, if you're deploying an application with a peer library inside it in AWS, then you could monitor some stuff, and when that stuff got to a certain number, you could have CloudFormation start more stuff. But, it's you doing it. It's not Datomic doing it for you.
Have you guys automated that for us?
No. So for the we value of you, we haven't. And there's a story behind this which sort of gets to the whole thing. Like we were really caught by the cloud twice in quick succession when we first launched Datomic. So some people have heard this story before. But when we first built Datomic, we wanted to target the cloud primarily, but there wasn't we didn't think that there was a suitable storage backend for what we wanted. And to make a long story short, what we wanted was something like DynamoDB, but DynamoDB did not exist yet. And so we built DynamoDB, right? We built a distributed, multiple process, multiple storage thing that had a lot of the semantics of DynamoDB. And literally 2 weeks before we were going to launch the initial release of Datomic, Amazon launched DynamoDB. And we looked at it and we said, the most craptaculous part of our story has been the operational overhead of managing this thing. And Amazon just made a great one. Let's take a week and figure out if we could drop that piece out of our system and replace it with DynamoDB. Well, the system was already designed to treat storage as a protocol. And, those of you who know a little bit of Clojure, we had a Clojure protocol for how storage worked. And we're like, okay, let's make that Clojure protocol point at Dynamo. So a week later, we were like, yeah, that's working. And a few weeks after that, we shipped. So an awesome story for the portability of good Clojure design and the use of Clojure protocols. Now, what happened right after we shipped? Right? There was much rejoicing at about this volume. Yay. And then there was a much louder, wow, that's really great, but I'm not using DynamoDB, and I'm not going to start using DynamoDB anytime now. So now we're like, okay, we just turned that way. Now we're going to turn back the other way and say, okay, well, we have a protocol. Maybe we could target other storages. And so then we targeted a bunch of other storages. Well, the thing about targeting a bunch of other storages is it vastly reduces the leverage of automating the kind of stuff that Jay wants, because every single one of our customers is doing something different. Right? If we only targeted DynamoDB, we almost certainly know that we're running in the cloud. So we can automate. If we make CloudFormation magic, it makes life better for 100% of our customers, because that's where they all are. But what happened is that our customers, we released, a half dozen or more different storage options, and our customers went out and evenly distributed themselves over some of those and completely ignored the others. And over the ones they equally distributed, those have all kinds of implications for if you were running on that storage, you're also doing this and also doing that. And so now there's no longer a good way for us to meet everybody where they are with that kind of automation, which is how Enterprise gets the extra 0 added on the right-hand side of the price tag, is all the variability. But there's a reason for it, right? It's all the variability in what people are doing and trying to meet them where all that variability is. So we'll talk more about storages in a second. Now, we still care about the cloud. We still are interested in doing more for our users who are running in the AWS cloud. So that's definitely the direction where we're looking to be. So caching. So I have said a couple of times, and usually people call me on this, but maybe people have heard this before now, and so people are getting wise to my trick. But I keep saying things like, transactions return the entire value of the database before and after. Well, let's say that your database has, 5 gigabytes of data in it. What does it mean when I say that I've returned the value of the database. I've returned the promise to be able to cough up the value of the database when you actually ask for it. And that's made efficient by having multiple layers of caching in Datomic. The peers have in memory what's called the object cache. The object cache is already materialized Java objects. They're actual things that implement an interface called datum. And they're lying there in your process, which means if you ask a question that's about those datums, how quickly can Datomic give you the answer? Right? Lickety-split, memory speed. On the other hand, if you ask questions about datums that are not already in memory, Datomic has to go and get them. Well, how far away are they? They're in storage or they're in memcached, depending on whether or not you added memcached. What happens when you add memcache to your Datomic system? What happens to your programs to take advantage of that? Nothing. Has anybody ever written code to actually specifically memcache this, that, or the other thing to make your program go faster? That's not a fun thing. It's not a place where you want to be. Right? This is an amazing thing. What do you have to do to an existing memcache to get Datomic to use it without conflicting with your other uses of memcached? Nothing. Datomic stores everything it stores in memcached under GUIDs that are not going to conflict with anything else. So you could just say, oh, look, we have this memcached over there. We don't even know what other people are using it for, but we'll just point some peers at it. You might hurt other people's performance characteristics. I'm not saying you should definitely do that. So you're going to hit memcached or you're going to hit storage, and how fast that is going to vary. Now, interestingly, we're all accustomed to getting these kind of performance speedups and not worrying about it. Most of you don't spend very much time worrying about how often instructions are in the L1 cache on your machine. You have a presumption, and it's a good one, that a high percentage of the time instructions are in the L1 cache. If that were not true, you would notice. Right? But that's managed for you, and it's completely magic. Right? It's completely automated. It's automated by various strategies and sort of guessing what instructions you're going to need. Well, Datomic does the same thing. Datomic manages segments of index, and it puts them in your peer process, whether it's the peer library in your application or the peer server, based on some guesswork about what you're going to need, and of course based about what you've asked for. Right? If you've asked for something, you clearly need it. But when you've asked for something, it's reasonably likely that you're going to need things near that, things like that. So Datomic does some stuff there, which means that caching is super easy. You really just have one knob. How much cache do I want? Datums are cached in segments, not individual facts. And so how many people have heard of what's called the N+1 problem, talking to a database? This was a big nightmare when EJB 1.0 came out. And what would happen was people that were talking to SQL directly would do sensible things. They would say, go get all the information I need. And then people used EJB in a naive way, and every time an EJB wanted to get a different attribute of the same entity, it would go and send out these really tiny SQL queries, and all of a sudden you'd get thousands of round trips to the database. Well, because Datomic segments have thousands of datums in them, you amortize the cost of ever hitting the actual storage at about 1,000 to 1 ratio. Right? At which point, it's effectively local now, right? Because you've amortized it out. So that's how this works. And the important key here is that the indexes are immutable, so segments never expire. Everything's immutable in Datomic. And because you have that 1,000 to 1 ratio, you don't have to worry about the occasional miss. Right? I mean, for many uses. There are still cases where the misses matter, as it is with your processor. Right? You can come up with loads on your machine where all of a sudden you'll notice the L1 cache misses being a problem. But in general, it's not a huge problem. So when you think about configuring your system, you're going to have object caches on the peer. Those are going to be formatted as Java objects, and the latency of getting to that stuff is microseconds or less. And you're going to be able to have 10 gigabytes or so per peer. And we're presuming that you're not going to do things like running a 100 gigabyte Java heap. Not that you couldn't, but there are all kinds of well-known challenges with running really big Java heaps in terms of garbage collection and so forth. So that's why that 10 gigabyte limit is not really a limit. Right? You can run bigger heaps, but there are challenges there. Then how much memcached are you going to run? Well, that's up to you. The data that's stored in memcached is in a format that's at least an order of magnitude smaller, if not more, than stuff in Java memory. Right? Because Java objects in memory are big, and we also can zip them and use freshen compression and things like that. The stuff that's stored in memcached is exactly the same as the stuff that's stored in storage. So this is behind all of your query and stuff. This is the physics that makes things work or not work. Chris?
Stuart, you mentioned that, I think on an earlier slide, that there's a dial for how much. I assume that's in cache, obviously, but the pure object cache as well, you can
Yep.
control that.
Yeah, there's a per process dial. So memcache is just you start the memcache process with whatever settings. And storage has whatever settings it has. We'll come back to it in a minute. In your process, by default, a peer process will start with half of memory allocated to the pure object cache. Because the presumption is that your application is dominated by doing database work. Right. So we're going to give a lot of memory to that, but that's a knob, and you set that with a system property. Okay. Now, you guys have asked a bunch of really good questions today, but you haven't really beaten on me very much about how can this be performant. So when we first started talking about Datomic several years ago, before people had a lot of positive experiences with it, we spent a lot more time talking about this slide. And I'll say it briefly, and if you have questions, we can say more. But basically the idea is, if you had an append-only database where you had to rewrite the underlying durable storage tree on every transaction and maybe compact it or whatever, that wouldn't perform very well. So we didn't do that. What Datomic does instead is it maintains recent history in memory in every process. And the amount of recent history that it maintains is on the order of 32 megabytes of Java objects. That's also configurable, but it's on the order of 32 megs of stuff, which means that expensive operation of rewriting the whole durable storage tree gets amortized out instead of on a per transaction basis, which might be a kilobyte or less, up to every 32 megabytes worth. And it's done in the background. So one, it only happens 1/100th or 1/1000th or 1/10,000th transaction, and two, it's done in the background, so you basically don't care anyway. So all the things that people worry about with append-only data stores have never been a problem for Datomic. It was designed with knowledge of the problems of those systems in mind from day zero. So it's just, but people have this. This is the thing people trot out and go, well, this can't work. So it can work, and this is why it works. And that background indexing job is today done in the transactor. So it does compete with transactions for resources. And so the transactor is typically a beefy enough machine. The transactor can probably use 3 or 4 threads just for transactions because it breaks the transaction. Even though it's a single writer system, it breaks the transaction work into a pipeline. And it can probably use a few more threads, 3 or 4 more threads for indexing. So you want to have a reasonably beefy transactor. Yes?
Did you just say that it's not returned to storage right away?
Oh my God, what did you say? Oh my God, the sky is falling. I'm sorry, say it again.
Did you just say that the data was not actually put to storage right away?
You could have inferred that easily by what I said. So easily, in fact, that you might imagine that I said it just to get this question. The index tree is not rewritten except for every 32 megabytes, but every transaction is written to the log as part of the transaction. Because we said this before. You tell me, I've got a transaction for you. The transactor says, let me think about that. Okay, I like that transaction. I'm going to write it to the log. And here's your answer. Right? The log is written on every transaction, but the log is not expensive. Right? The log is just chugging down storage, writing stuff. But rebuilding the index trees is done on an amortized basis. And that's part of the, it's not actually the coolest part of the secret sauce, but it's an important part of the secret sauce. It's certainly a requirement to make a system like Datomic work. You can't rebuild the index tree on every transaction, but you do have to write on every transaction. When you phrase it that way, the solution's obvious. Write on every transaction, but don't rebuild the index tree on every transaction, which is what Datomic does. This does mean that every time a peer connects to Datomic, it will rebuild the most recent stuff itself. Each peer does this. It's called catch-up. And so it will rebuild the most recent. On a loaded system, I would say on average it's going to be not 32 megs, but 10 or 15. It will rebuild that stuff on catch-up. And you'll see that it's actually logged how much time that takes, but it's fairly negligible. Right? It will slurp that most recent portion of the log and rebuild the index itself. Because the durable index hasn't done that yet. Right? It's in the durable log. It's not in the durable index. So Datomic's trees are persistent data structures. For those of you who've come in and were in the closure class earlier, they are persistent in the sense that they are durable, and they are persistent in the sense that they are accumulate only, and they, newer versions incorporate data from the older version. They are very akin to the persistent data structures that Clojure itself uses, except that they have a really wide branching factor. The branching factor is on the order of 1,000, and there are 3 levels in the tree. 1,000 times 1,000 times 1,000 is 1 billion. So you can put 1 billion things in Datomic without the root node starting to gain weight. After you put 1 billion things in Datomic, the root node starts to be bigger than the other nodes because it never splits, which is also fine. You can still put 10 billion or 100 billion things in Datomic. You're going to have a fat root node, but that's okay. So index is done in the background. Indexing is fast enough to keep up with the ongoing writes of a system, a Datomic system, that is within the size boundaries that we recommend. Right? In other words, which I'm going to come to in a second. Right? Which, just if you want to put a number on the wall, is 100 billion. Right? If you have more than 100 billion facts, don't put it in one Datomic system. Put it in more than one Datomic system, or Datomic is not suitable for you. If you have less than 100 billion facts, then it's reasonable to talk about putting in a Datomic system. If you're only going to put 100 billion facts in a Datomic system, and it's going to be an ongoing system that's going to run for years, then you're not going to hit a point where indexing falls too far behind and you can no longer accept transactions, except if you have a burst of writes. If you have and the primary place where people have a burst of writes is when they're doing their initial import. So if they're building up a Datomic system from an existing system, they might, during that initial import, get to a point where the indexing job in the background says, hey, I can't keep up. And the foreground says, well, I don't want to hold more memory than that because you've told me, I don't want to go bigger than a certain amount of stuff in memory on every peer. Then you're going to get a distinguished behavior, which is that the transactor just slows down taking writes. It doesn't stop. It just starts taking a lot longer to do writes until the background indexing job can catch up. And you can go and look on the internet for people doing import jobs, and you can see, the performance characteristics of that happening. And when that happens, you get a metric. If you're in CloudWatch, and Datomic also has a pluggable metrics API, so you can get it other places if you want. And you can see that happening, and you can say, my system is under more load than is sustainable in the long run, so we got to slow down. So you can see that happening. You can try it out with your data, what have you.
Can you just increase your memory for doing an import?
You can increase your memory for doing an import up to a point, right? So remember we said that each peer is going to maintain some window of memory, but you can't increase that arbitrarily. So there are definitely write scale systems for which Datomic is not suitable, and for which neither import nor ongoing use, for which Datomic makes sense, like dumping all your log files. Right? Datomic is not the database to put all your log files in, as a for instance. All right. Now we're going to talk about storage, right? We've just ignored storage. By the way, all of the storage that you've accessed today is local storage on a disk on Marshall's laptop up there. That's called dev storage. Dev storage uses a SQL database running embedded inside the transactor. What is that good for? No. Dev. What do we say when you call support in the middle of the night and you say your production system is down and we ask what storage you're using and you say dev? Bye. It's not for production. So then the question is, what is for production? And the answer is there are 3, one of which has a bunch of sub-bullets. DynamoDB, which was the second storage we targeted after our homegrown storage, which we never shipped. SQL, of which there are many flavors, right? SQL uses JDBC. Predominantly, people out in the wild, as you might imagine, use Oracle, SQL Server, or Postgres. And I guess we have people using MySQL as well. A handful. And then Cassandra. Right, and people run those on RDS. That's right. So people run on RDS, but they don't want DynamoDB. They use one of the others. And then Cassandra. There are other storages that we have supported in the past, including Couchbase and Riak. Those are now classified as legacy storages, and we support them for enterprise contracts, and we encourage people that are getting started to go to one of these. These are the ones that experience have proven, one, that they're the ones that people who have actually used the system have chosen by about 2 orders of magnitude compared to the others. And they are therefore, and for other reasons, the easiest ones to support cost effectively. So these are the places where we recommend that people go. How do you choose which storage you're going to run on? My primary recommendation is actually the third bullet here under important, familiarity. You should choose the storage you know how to operate. That is going to dominate typically. But in addition to that, I would say manageability, which is a way of saying that again. Right? Pick the one that you know how to operate. And reliability. You should run a storage that you feel good about. Right? All of those storages we feel pretty good about. But you should pick the one that you feel good about. Less important is the performance behavior of storage, because Datomic substantially insulates you from storage performance, both on reads and writes. It insulates you from storage performance on reads because you can strap on memcached, right? And you sort of, and that's the recommended thing to do to make reads fast, not to try to pick a fast storage. It insulates you from writes by being a single writer system. So it's hard for the, Datomic can't make Cassandra or DynamoDB fall down and cry, right? It's not going to. It's a single writer system. It's just not going to make those things cry. And it's not even likely to make a traditional SQL fall down and cry. Now, admittedly, your transactor, if you're provisioning it yourself, if you're running Cassandra yourself, if you're running Dynamo, you can't run Dynamo yourself, if you're running SQL yourself, you should provision a sensibly beefy box, which would always have been true anyway. That Datomic has a stellar track record of remembering your data. And the one place where we've seen people have any trouble, the biggest trouble we've seen people have, and this is a useful thing to know, is that Datomic is likely to turn your storage problems from data loss into an availability problem. Right? Because Datomic is just going to stop. Right? Datomic's going to say, well, that thing is not capable of, I tried to ask it to do something, it said I couldn't do it, and Datomic is going to say, I'm done, and the transactor is going to shut down. Right? It's going to turn. So by far, of the sort of dozens of sort of major level support calls, almost all of them have been Datomic turned your underlying storage problem from a possible data loss problem into an availability problem instead. Which again is consistent with our values, right? That's where we want to be, right? We don't want you to lose data. But if you are hell bent on losing data, right? Misconfiguring your storage to drop your data, right? If Datomic's talking to your storage and you tell storage to lose data, which there are ways to do, right? Again, I think this is crazy, but everyone's in like this benchmark game to be fastest, and so there are configurations of storages that are just not durable, right? If you configure your storage not to be durable, then in order to get the fastest benchmark performance, then we can't fix that.
I do believe that every member of the Cognitive team who's ever been involved in support tickets now flinches when you hear the phrase replication factor.
Well, as long as it's, unless
Well, no, if it
it's
comes
followed
up
by
on
a
support
large
ticket, we're
number,
like, oh.
right? You're like, what's your replication factor? Oh, I don't know, 2.
Right.
That's not good.
I would also say, and I hate to be mean, but I trust Amazon better to manage DynamoDB than I trust any of you to manage Cassandra or Oracle or SQL Server. And that's just based on experience, right? We have never had a customer say, Amazon screwed up Dynamo and therefore we lost data. Right? It's just not going to happen. I mean, it could, right? Obviously, but it's never happened.
That makes the manageability part a lot more approachable for someone like me who is happily unfamiliar with all the options. So I might start there. If I needed to get a production system in over a weekend.
I like DynamoDB.
Yeah.
I mean, you're going to want to run the code in AWS if you're running against DynamoDB from a latency perspective, right? You're going to want to run the code on AWS. So that, and so if you're not familiar or comfortable with any of them, right? Install run on AWS against DynamoDB, or pick a SQL thing that that doesn't look that hard to get installed and use it with its default settings. That's the other thing. SQL World comes from the same side of the CAP theorem that Datomic does, so their default settings are more likely to be we're not going to lose your data. Whereas the NoSQL world is much more going to be likely like we're going to have some kind of default settings that are good for winning benchmark games. And so, more of a challenge there. All right, enough of that. So you need to understand that a Datomic system is a single writer system, but you do not want your system to become unavailable for writes because one process died. And so when you deploy Datomic, you can have as many or as few peers as you want. You probably want at least one, otherwise you can't talk to the system. But you're going to probably want to have at least 2, and at most 2, transactor processes live at any given time. And the reason for this is that Datomic, out of the box, when you start running 2 transactors, what happens is those transactors will race. So let's imagine you have a Datomic system that's currently down, not running at all. And you start 2 transactors. Those 2 systems are going to race. One of them is going to win the race and is going to become the active transactor. The other is going to lose the race and it's going to become the standby transactor. And now, off you go. They coordinate to know that the active transactor is still alive through storage by doing conditional operations against storage. The active transactor says, conditionally, that was the old status of the storage beacon. I'm updating the storage beacon and saying, I'm still alive, I'm still alive, I'm still alive, I'm still alive. The standby transactor is reading the storage beacon saying, is she still alive? Is she still alive? Is she still alive? Is she still alive? And if the standby transactor decides that the active transactor is not alive, which means it's missed 2 beacons, then it's going to say, oh, I'm taking over. It's going to start writing the beacon. It's also going to start taking transactions. Now, there are several nice things about this. One of them is it's not replication of any kind. Right? How much storage is the transactor responsible for? Nada. It knows nothing. I mean, it's going to do all this talking to storage, but it's not responsible for any of the storage. So for the standby transactors to stay in, it doesn't stay in sync. It just waits until there's a problem, and then it's like, okay, now I'm jamming. So you don't have to worry about, right? This is not some sort of complicated coordination mechanism. And the other thing is, if, and we haven't, but if we completely screwed up the HA handoff mechanism, could we accidentally have 2 writers in the system? And the answer is no, right? Because the whole beacon mechanism that allows one transactor to take over from another is a conditional write of the beacon, and the actual mechanism for writing transactions is a conditional write of a thing called the log tail, right? And so if we completely screwed up the beacon logic, the worst thing that we could do is make a system that became unavailable because transactors were constantly starting and dying and starting and dying and starting and dying, and maybe screwing up racing to talk to the beacon in some way. Even if that system was completely screwed up, you still couldn't have multiple writers at a time. Right? There's exactly 1 line of code in the entire system that runs on 1 thread that does that job. And so we had to QA the absolute bejesus out of that 1 line of code. And now we're like, hey, look, we're never going to have 2 writers in the system. Yay. Which is really great. Right? It is, and it's a trade-off, as we'll see in a minute. There's a trade-off that comes with that. But the trade-off includes a lot of peace of mind about the underlying robustness of the core system. So Datomic, you can't really see this slide in any detail, but what this is showing, and you can look at, I'll drop the slides in a repo where you can grab them. What you can see when you look at this more closely is that all the different components of the system produce a bunch of metrics, and so you can monitor the system in CloudWatch and see that what the transactor is doing, what the query is doing, and so forth. Also, again, this is we started with CloudWatch, but then everybody was like, well, I'm not an AWS. There's a callback API, so you can implement the metrics yourself and do whatever you want. So that's enough of that. Capacity planning. How much data should you put in a database? If you're going to put more than 10 billion datums in a database, then please call Marshall during the design process, and we can talk through the challenges of running in what I would call a large Datomic database, 10 billion datums or bigger. If you're going to put more than 100 billion datums in a Datomic database, just don't. Right? Come up with a different plan. And this is the fundamental. Datomic is not a write scale system. The write volume in the system should be consistent with ending up at not bigger than your data size.
By when?
By when you want to retire your system. So I usually use 10 years. So if you're going to write, substantially more than 10 billion datums a year, then you're going to end up at over 100 billion datums, and you should call us and say, here's what if you feel like you're on the edge of that, you should call us, because there's no hard limit. Right? There's definitely not a hard limit in the system anywhere. But there are challenges, as in any system, there are challenges in running a larger system compared to running a smaller system. On the read, let me finish all this. On the read side, right, Datomic is a read scale system. Right? Reads happen separately from writes, which means you can scale those independently. So it's a read scale system. So if you have a system that reads more than it writes, Datomic may be a good fit for you. A large number of systems that are information systems, that are systems of record, are read vastly more than they're written. Right? You write a fact into the database once and you read it hundreds or thousands of times eventually. Datomic is a good system for that. It is not a good system for data that is written more than it is read. And this is the capture everything and maybe it someday will matter kind of system, right? So you're throwing all of your logs somewhere, and then you might go back and map reduce over them to find a problem. You don't even know what you might look for, right? It's schemaless. It's a pile of stuff. It's not necessarily garbage, right? It's mostly coal, but there are some diamonds in it somewhere. You don't even know what they're going to be, but you might map reduce over it later to look for stuff. That's not a good fit for Datomic. Housekeeping-wise, you need to garbage collect both Datomic and underlying storage, and we have instructions for doing that. That has not been a big problem for people. That could have big scare quotes around it, but it doesn't. The 100 billion datums should have some scare quotes around it. If you want to put a trillion datums in the system, it's not going to work. Don't do that. But the housekeeping stuff does not have scare quotes around it. Caching, you need to understand the physics of your own data. So if the hot sets in your data fit easily in the object cache on individual peers, then you don't really need to add memcached. If your underlying storage is crazy fast, you don't need to add memcached. If those two things are not true and performance matters to you, then you should test and monitor and maybe add memcached.
And many performance tickets start with us saying, did you turn on memcached? And somebody saying, I didn't bother. Please bother. Oh, ticket's off.
Well, on the other hand, though, a lot of performance tickets, a lot of performance conversations, forget tickets. Performance conversations start with, I want it to be infinitely fast. And the answer is no, you don't. Right? Just like you don't buy a car that's capable of setting the land speed record. Right? There are other concerns, and that car is really expensive and it's not very good for other things. So it's really a matter of, and the big one I would say is, if you don't care enough about performance that you have an SLA and you regularly measure against it, then you don't care about the performance that much, which is fine. It's great. Most systems are built not caring about performance that much because it's not the dominant factor, and that's awesome. If you do care about performance enough to measure and have an SLA, and you want to know if Datomic's a fit for what you're doing, then call us and tell us what your SLA is and how you're measuring it, and happy to have the conversation. All right. So, how to end. Here's some things Datomic is not good for. It's not a write scale system. Don't dump your logs in it. Don't dump all of SETI in it. Right? It's not for that kind of thing. It's not suitable for storing media. Don't store audio or video or arbitrarily large Word documents in it or something like that. It's not suitable for that. It's not suitable for churn, like a hit counter. Hit counter is not something you care about the history of. I can tell you what the hit counter's value was before it was 99. It was 98, but you don't care. Right? You care about the aggregates. You don't care about the, right? So it's not a big data system. It's not for graphics, it's not for video, it's not for log file analysis. Datomic is a good fit for information of record, information that you care about, information that you're likely to read more often than you write, information that you're likely to ask questions about in different ways. It's a great system for dev and ops flexibility because of the way it's broken apart, because there's storage and transactions and read, and they're all separate. It's great if you care about history. It's great if you need to scale reads. It's great for transactional data. It's great for business records, medical records, scientific records, inventory, configuration data, web applications, departmental databases, apps that are going to run in the cloud. So there are a lot of different domains where Datomic is suitable. And your final lab, which you're going to have to do at home because we're going to close, is to go back and look at those characteristics and look at the characteristics of the sample app you built today and say, how good would Datomic be at this, and compared to what? And I would give you one piece of advice how to do this. This is, the classic Rich Hickey standard on everything. Make a table that has pluses and minuses, right? So many of these conversations are all about benefits, right? This, and this are good, so I'm going to do it, right? That's not a good way to make decisions. There are going to be pluses, there are going to be minuses, and those pluses and minuses are going to be situated by your problem, and they're also going to be situated in comparison to other things. We think Datomic is a nice default for a lot of systems of record, and it's not awesome for other things. And we hope that you'll find it to be so too. If you're having trouble remembering what axes to put on the comparison, I'll drop a slide with a whole ton of words on it. And these are all things that you might want to think about to ask yourself, did you capture everything that happened this week? And if you're not sure if you did, I'm going to drop the slides tonight. I'll send you a link in the Slack, and I'll also drop a link on Twitter. I'm happy to take your questions. I think we have to shut down here, but we'll all have a big happy hug, and then I will go and stand out in the hall and take questions for as long as we want. This is the end of the day of Datomic. You get a day of rest or maybe a day of Clojure Spec tomorrow, and then we're off to Clojure Conj. Thank you.